The goals of our report are the following: to define a cooling tower and to describe each of its type, to enumerate and discuss its components, to illustrate the mechanism of a cooling tower, and to solve problems regarding cooling tower.
Cooled water is needed for air conditioner manufacturing process or power generation. A cooling tower is equipment used to reduce the temperature of a water stream by extracting heat from water and emitting it to the atmosphere. The figure shows what the cooling tower is. Components of a cooling tower. Most towers have structural frames that support the exterior enclosures, motors, fan, and other components. With some smaller designs, such as some glass fiber units, the casing may essentially be the frame. Most tower employs fields, which is made of plastic or wood, to facilitate the heat transfer by maximizing the water and air contact. There are two types of field: splash field, which water flows over the successive layers of horizontal splash bars, continuously breaking into smaller droplets while also wetting the field surface. Plastic splash fields promotes better heat transfer than the wood splash field. Film field consists of thin, closely spaced plastic surfaces over which the water spreads, forming a thin film in contact with the air. This surface may be flat, corrugated, honeycomb, or other pattern. The film type of field is the more efficient and provides same heat transfer in smaller volume than the splash field. Cold water basin is located near at the bottom of the tower. It receives the cooled water that flows down through the tower field. The basin usually has a sump or low point for the cold water discharge connection. In many tower design, the cold water basin is beneath the entire field. In some forced drop counterflow design, however, the water at the bottom of the field is channeled to a perimeter trough that functions as a cold water basin. Propeller fans are mounted beneath the fields to blow up the air through the tower. With this design, the tower is mounted on legs, providing easy access to the fans and their motors. Drift eliminators. This captures water droplets entrapped in the airstream that otherwise would be lost to the atmosphere. The air inlet is the point of the entry of the air entering the tower. The inlet may take up an entire side of the tower for cross-flow design or be located on the side of the bottom of the tower for the counterflow design. Louvers. Generally, cross-flow towers have inlet louvers. The purpose of the louvers is to equalize the air into the field and retain the water within the tower. Many counterflow tower designs do not require louvers. Nozzle sprays water to wet the field. Uniform water distribution at the top of the field is essential to achieve proper wetting of the entire field surface. Nozzles can be fixed and sprayed in a round or square pattern, or they can be a part of the rotating assembly as found in some circular cross-section towers. Fans, which is both axial, propeller type, and centrifugal, are used in towers. Generally, propeller fans are used to induce draft towers, and both propeller and centrifugal fans are found in forced draft towers. Depending upon their size, the type of the propeller fan used is either fixed or variable pitch. A fan with non-automatic adjustable pitch blade can be used over a wide kilowatt range because the fan can be adjusted to deliver the desired airflow to the lowest power consumption. Automatic variable pitch blades can vary airflow in response to changing load condition. Types of cooling tower. The natural draft or hyperbolic cooling tower makes use of the difference in temperature between the ambient air and the hotter air inside the tower. It works as hot air moves upward through the tower and fresh cool air is drawn into the tower through an air inlet at the bottom. Due to the layout of the tower, no fan is required and there is almost no circulation of hot water that could affect the performance of the tower. concrete is used for the tower shell with a height up to 200 meters. These cooling towers are mostly only for large heat duties because large concrete structures are expensive. There are two main types of natural draft tower. The cross-flow tower, in which air is drawn across falling waters and the fill is located outside the tower, and the counterflow tower, in which air is drawn up to the falling water and the fill is therefore located inside the tower, although design depends on the specific site conditions. Mechanical draft cooling tower have large fans to force the draw of the air through circulated water. The water falls down over the field surface, which help increase the contact time between the water and the air. These help maximize the heat transfer between the two. Cooling rates of mechanical draft tower depends upon various parameters such as fan diameter and speed of operation, fields for system resistance, and etc. Mechanical draft tower are available in large range of capacities. Tower can either be factory built or field erected. For example, concrete towers are only field erected. Many towers are constructed so that they can be grouped together to achieve the desired capacity. Thus, many cooling towers are assemblies of two or more individual cooling tower or cells. There are three types of mechanical draft cooling tower: the forced draft, induced counterflow draft, and induced draft cross-flow. Forced draft cooling tower is a tower in which air is blown through the tower by a fan located at the air inlet. The advantages includes suited for high air resistance due to centrifugal blower fans. Fans are relatively quiet. The disadvantage are recirculation due to high air entry and low air exit velocities, which can be solved by locating towers in a plant room combined with discharge ducts. The two types of induced draft cooling tower are cross-flow and counterflow. The advantages of the induced draft cooling towers are less circulation than forced draft towers because the speed of the exit air is 3 to 4 times higher than entering air. The disadvantages are fans and the motor drive mechanism require weatherproofing against moisture and corrosion because they are in the path of humid exit air. In the induced draft counterflow cooling tower, the hot water enters and exits at the top and uses forced and induced draft fans. The induced draft cross-flow cooling tower operates in a way that the water enters at the top and passes over the fill, and the air enters on the side of the tower. The induced draft cross-flow cooling tower operates in a way that water enters at the top and passes over fill, and the air enters on the side or opposite side, and the induced water draft fan draws air across the fill towards the exit at the top of the tower.
The performance of cooling towers is evaluated to assess present levels of approach and range against their design values, identify areas of energy wastage, and to suggest improvements. The measured parameters include wet bulb temperature of air, dry bulb temperature of air, cooling tower inlet water temperature, cooling tower outlet water temperature, exhaust air temperature, electrical readings of pump and fan motors, water flow rate, and air flow rate. These measured parameters and then used to determine the cooling tower performance in several ways. These are range, approach, effectiveness, cooling capacity, evaporation loss, cycles of concentration, blowdown losses, and liquid gas ratio. The range is the difference between the cooling tower water inlet and outlet temperature. The formula for cooling tower range in degrees Celsius is cooling water inlet temperature minus cooling tower water outlet temperature. A high cooling tower range means that the cooling tower has been able to reduce the water temperature effectively and thus performing well. Approach is the difference between the cooling tower outlet cold water temperature and ambient wet bulb temperature. The formula for approach is CD approach in degrees Celsius